Cool. I'm gonna get started. So, chapter 7 homework is due today, the 23rd. The chapter 7 quiz is today in SI. That's your last quiz. Then we will have the tests next in a week on Wednesday. Same as all the other tests, you get one sheet of notes that you can use. Monday next week, we will be doing the review of chapters 5, 6, and 7. And if the lab period on Monday next week is for makeups. And so now let's go through there, chapter 10. So we're going to talk about nuclear physics. We'll talk about what's important about we'll talk about the atomic nucleus is really important to our modern society, it turns out. I mean, if nothing else, understanding what the majority of atoms are made of, like most of the mass of an atom is in the nucleus. So it's important for things like, we use it for the diagnosis and treatment of cancer and other diseases. We use it for geological and archaeological dating. We use it for chemical analysis. We use nuclear energy and nuclear disposal, we're going to talk about. We'll talk about the formation of new elements, the radiation of solar energy, and the generation of electricity. So there were early thoughts about the elements. Greek philosophers were the first people to speculate about the basic substances of matter. Some of them came to the assumption that everything was made of like indivisible parts that they called atoms. And Aristotle speculated that all matter is composed of only 4 elements: earth, air, fire, and water. He was wrong. But that's what you get when you're on the experiment. So it turns out that there are, I don't know, 100-odd elements. There are 90 or so that are naturally occurring on Earth. And it turns out we can identify separate elements, and different elements have different nuclei, basically. So the Swedish chemist, John Jacobs Berzelius, in the early 1800s, used 1 or 2 letters of the Latin name to designate each element. So here are some of the chemical symbols that are still around that come from Latin names. So for copper, it's Cu from the Latin name cuprium. For gold, it's Au from the Latin name aureum. For iron, it's Fe from the Latin name ferrum. For lead, it's Pb from the Latin name plumbum. For mercury, it's Hg from the Latin hydrogarium. For potassium, it's K from the Latin name kalium. And since Berzelius's time, most elements these days have been symbolized by the first 1 or 2 letters of the English name. So a lot of elements, like silicon is Si for silicon. You aren't expected to know anything, but this is a table of some common elements that might be useful to know. We'll just keep going. So all matter is composed of atoms. And an atom is composed of 3 different types of subatomic particles. There are electrons, protons, and neutrons. Electrons have a negative charge, protons have a positive charge, and neutrons are neutral. And the nucleus of the atom contains all the protons and neutrons, and is tiny compared to the rest of the atom. And the outside of the atom is the electrons. The electrons surround and orbit. The common term is orbit, but they surround the nucleus. They're attracted to the nucleus because they have an opposite charge from the nucleus, and then they fill up energy levels there. So electrons and protons have equal but opposite charges. So a normal neutral atom will have an equal number of protons and electrons. The interaction of electrons is what causes chemistry. So all the chemistry you've heard about, forming chemical compounds, things like that, that is the interaction of electrons with other electrons. It's all stuff on the outside. But today we're going to talk about the nucleus, the middle, the major constituents of an atom. The electron, which has a charge of minus 1.6 times 10 to the minus 19. The proton, which has a charge of plus 1.6 times 10 to the minus 19. You know, minus 1 and plus 1 in the quanta of charge, the base units. And you'll notice that the proton and the neutron are about the same mass, and the electron is much smaller. It's about a 2,000th of the mass of a proton or a neutron. Nim? So protons and neutrons have nearly the same mass. They're about 2,000 times more acid than the electron. And so the electron was discovered by J.J. Thomson in 1897, the proton by Ernst Rutherford in 1918, and the neutron by James Chadwick in 1932. The electron was the easiest to discover because it's on the outside. The proton and the neutron were harder to discover because they don't float around on their own. And the neutron was, of course, harder because it's neutral. And so J.J. Thomson thought that there were positive charges and negative charges, and everything was sort of evenly mixed. There were these electrons throughout the dew of positive charge. This was called the plum pudding model. And Ernst Rutherford did an experiment where he shot alpha particles at a thin sheet of gold foil. And the thought was, okay, we have a thin sheet of gold foil. We think this is made of some, basically made of some positively charged goo with some little electrons scattered throughout it. What happens if we shoot these alpha particles at it, these big, heavy particles? Well, the thought was basically they just go through. But what was shocking was some of these alpha particles bounced back. So I think a description of this was like, it was like shooting a gun at a piece of tissue paper and the bullets bouncing back. This was not what people expected. An alpha particle is actually a helium nucleus, by the way. And they're a readily available source because certain types of nuclear decay emits alpha particles. Now, 1 of every 20,000 alpha particles bounce back. And Rutherford can only explain this by assuming that each gold atom had its positive charge all concentrated in a very small nucleus. And the nucleus is tiny. It's about a 10,000th the size of an atom. So the diameter of a nucleus is about 10 to the minus 14 meters, while the diameter of the whole atom, the outer electron orbits, is about 10 to the minus 10 meters. But 99.97% of the mass of an atom is concentrated in the nucleus. Because, you know, electrons are like 1/2000th of the mass of protons and neutrons. The atomic mass is much more concentrated in the nucleus. So what we have is we have a ball with electrons sort of flinging about in a tiny super dense object in the middle. So the volume or size of an atom is determined by the orbiting electrons. The diameter of an atom is about 10,000 times bigger than the nucleus. And if you could pack nuclear material, protons and neutrons, into a sphere the size of a ping pong ball, it would have a mass of 2.5 billion metric tons. Now, it turns out in outer space, there are things that are made of densely packed nuclear material like this. They're called neutron stars. They're some of the strangest things in existence. And if they get too big, they collapse under their own gravity to form black holes. So, you know, they're about as dense as you can get. So this is a visual representation of a nucleus. It's a bunch of protons and neutrons packed together in a tiny, tiny space. And the way we describe a nucleus, we use 2 numbers. There's the atomic number, which is the number of protons in the nucleus. This defines what element you're talking about. So hydrogen, for example, always has one proton in its nucleus. Name? Helium always has two. Lithium has three, and so on. Carbon has 6. Oxygen 8. That's the atomic number. That also designates the number of electrons that element normally has. If an element either gains or loses electrons, it ends up charged and is called an ion. You may have heard of ions or ionosphere or things. For example, if a sodium atom loses an electron, it becomes a sodium ion. That's actually how salt is formed. Sodium atom loses an electron, the chlorine atom gains an electron, they're attracted to each other, and that forms sodium chloride, salt. Now, the other number we use to describe nuclei is the atomic mass, the mass number. This is the total number of protons plus neutrons. And this number also more or less corresponds to the mass of the atom. The electrons barely weigh in. So the total number of nuclei, protons plus neutrons. And for the same element, you can have isotopes. You can have versions of that element where they have different numbers of neutrons. Name? So you can have an element with different numbers of neutrons. And we call it the same element because its normal number of electrons is the same, so it has the same chemistry. It generally acts like that element. It just weighs a little bit more or a little bit less. But that's important when you worry about what nuclear things are going to happen. So the way we write this, you write the mass number up on top here and the atomic number down on the bottom here and the chemical symbol here. The chemical symbol and the atomic number are tied to each other. So the chemical symbol, so this is often dropped and the chemical symbol tells you what it would be. But for example, I could write, so this is an isotope of helium, helium-3. The most common isotope of helium is helium-4, which you would write like this. And these are commonly written just, you write the 3 for the mass, and you leave off the number because the helium tells you the atomic number. You could also have, various others. So some elements have several isotopes, like carbon. So the most common type of carbon is carbon-12. But there is also carbon-13, which makes up about 1% of the carbon out there, and carbon-14, which makes up even less. So isotopes of a single element have the same chemical properties. All those carbons are going to act the same, but they have different masses because they have a varying number of neutrons. And so because their masses are a little bit different, they can act a little bit different in reactions. The effect is strongest in smaller elements because then the change is more of it. Like, there's a big difference between hydrogen 1 and hydrogen 2 because the mass doubles. You have a significant effect there. But mostly the chemistry is the same. But again, in general, chemistry is almost identical. There can be some slight differences. So for example, in naturally occurring hydrogen, 1 atom in 6,000 is deuterium, and 1 atom in 10 million is tritium. So deuterium is hydrogen 2, tritium is hydrogen 3. And if you want to, you can concentrate the deuterium. There are reasons you might do this. So for example, in the big lab across the hall, because it turns out that for certain ways of studying, there's something called heavy water, D2O, which is water where the hydrogens have been replaced with deuteriums. We have a bottle of heavy water in the lab across the hall because it's useful for measuring things with NMR. Because you're looking at deuterium, the deuterium doesn't interfere with what you would normally be looking at. So if you want to determine the composition of an atom, let's say you're looking at fluorine 19. So fluorine 19. Fluorine has an atomic number Z of 9. So it has 9 protons and 9 electrons. Its mass number is 19. So to figure out the number of neutrons, you subtract the mass from the atomic number. So 19 minus 9 gives you 10. So fluorine 19 has 10 neutrons in it. So in the nucleus, there are protons and neutrons. The electrons orbit around the nucleus. The mass number, A, is the sum of the number of protons and neutrons. The atomic number is the number of protons. The neutron number, N, is the number of neutrons. And an isotope is an element with a different number of neutrons, but the same number of protons. So you can have various isotopes of the same element. The element is determined by the atomic number, the number of protons. The isotope is determined by having different masses, and they're named after the mass. And the atomic mass you see like on a periodic table is the weighted average mass of an atom of the element in a naturally occurring sample. So, for example, the atomic mass is measured in AMUs. The carbon-12 atom is used as the standard. It's assigned an atomic mass of exactly 12 AMUs. And the weighted mass of all carbon is slightly higher than 12, 12.011, because there's some carbon-13 and some carbon-14. And this is why, you get things like chlorine, which is like 35.5, because it's a mixture of chlorine 35 and chlorine 37. And then there's beryllium, which is about an even mixture of but it's even a mixture of 2 isotopes, more or less. So the fundamental forces of nature, there's 4 of them. We've talked about, well, there's gravity. The ones you interact with on an everyday basis are gravity and electromagnetism. The other 2, the strong nuclear force and the weak nuclear force, primarily deal with the nucleus. They're short range. So the electromagnetic force between a proton and an electron is 10 to the 39 times greater than the gravitational force between those 2 particles. So when you're dealing with small particles, gravity is negligible. So electromagnetic forces are the only important force on electrons, and they're responsible for the structure of atoms, molecules, and pretty much every force you feel on a day-to-day basis, other than gravity, is electromagnetic in nature. But the reason you don't explode, what holds together the nuclei in your body is the strong nuclear force. So the nucleus of any atom is extremely small and packed with neutrons and protons, which are all positively charged. So the nucleus, from electromagnetic force, wants to fly apart. It turns out it's held together by the strong nuclear force. There's a third fundamental force that somehow holds the nucleus together. This is the strong force, which is attractive at distances less than about 10 to the minus 14 meters. It's a little complicated. The strong force is more complicated than like the electromagnetic force, but that's the general idea. It really only matters at distances about 10 to the minus 14 meters. So for a large nucleus, the forces get complicated. You have an individual proton that's only attracted by the closest 6 or 7 nucleons, but it's repelled by all the other protons. because of the short distance nature of the strong nuclear force. So when the number of protons exceeds about 83, the electrical repulsion overcomes the nuclear force, and the nucleus will be unstable. So spontaneous disintegration or decay can occur in anything, will occur in anything with a number of protons greater than about 83. Now, that may take a long time, but it will happen. And certain isotopes are more stable than others. So even very small nuclei can be unstable if their isotope is not like a stable setup. So for example, tritium, helium-3, not helium-3, tritium, hydrogen-3 is actually unstable. It has too many neutrons. And so it will undergo radioactive decay. And that radioactive decay process is mediated by what's called the weak nuclear force. So physicists have also identified a weak nuclear force within an atom. This is another very short-range force. It reveals itself principally in the process of beta decay. So beta decay is the process by which a proton turns into a neutron or vice versa, and emits an electron or an anti-electron. And it's weaker than the strong force and the electromagnetic force. Hence why it's called the weak force. It's stronger than gravity, because gravity is just super weak. So the three known atomic forces, they're electromagnetic, weak nuclear, and strong nuclear. There's a single unified theory for them called the Standard Model. And we've also shown that at high enough energies, the electromagnetic force and the weak force merge to become one force. And it's thought that it will also merge with the strong force at even higher energies, but we've never actually managed that. So again, the mass number is the total number of nucleons. An isotope is what the number of neutrons vary in the nucleus of a given element. Any element is determined by the number of protons, and the atomic number is the number of protons. So radioactivity or radioactive decay is the process of the spontaneous process of a nuclei undergoing a change by emitting either particles or rays. So a nucleus, a specific type of nucleus like uranium-238 or carbon-14, will undergo some process of decay. So radionuclides are radioactive isotopes or radioisotopes. These are isotopes that will undergo spontaneous decay. And substances that give off that type of radiation are said to be radioactive. So the process of radioactive decay, there's the parent nucleus, the original nucleus before decay, the daughter nucleus, which is the resulting nucleus after decay, and radioactive nuclei can decay in three common ways. These are called alpha decay, beta decay, and gamma decay, named after the first three letters of the Greek alphabet. And there are alpha particles, beta particles, and gamma rays. Alpha decay is when a nucleus disintegrates into a nucleus of another element by emitting an alpha particle. It goes, I am too big, I am going to spit off a lump of my nucleus to fly out into the universe. An alpha particle is a helium nucleus. It's 2 protons and 2 neutrons. So alpha particles are relatively big. So they do a lot of damage if they hit something, but they're also really easy to block. So things that emit alpha rays or emit alpha particles, they're not super dangerous as long as you don't eat them. They're really, really bad if you eat them. If they get inside your body, they do a whole lot of damage. But outside your body, they're basically stopped by the air in your skin. Beta decay is a process where a neutron is transformed into a proton with the emission of a beta particle. And a beta particle is an electron. You could also have the opposite process where a proton turns into a neutron and emits an positron, an anti-electron. That's the other type of beta decay. And lastly, gamma decay occurs when a nucleus emits a gamma ray and becomes a less energetic form of the same nucleus. So gamma decay usually happens after something like alpha decay or beta decay. Things settle down and emit gamma rays. So they're somehow energized by something. You know, they spat something out that had a higher energy state, and they settle down by emitting a gamma. And you can identify the particles because alpha particles are positively charged, beta particles are negatively charged, the gamma rays don't have any charge at all. So if you put them in an electric field, alpha particles will go one way, beta particles will go the other way, gamma rays will go in a straight line. Or if you put them in a magnetic field, same thing will happen. Alpha particles will rotate one direction, beta particles will rotate the other, and gamma rays will keep going in a straight line. So here's an example. Thorium-232 decays to radium-228. You see how it lost 4 from its atomic mass and 2 from its atomic number by alpha decay, emitting a helium nucleus, which has a mass of 4 and 2 protons. You can then also have beta decay. That's what carbon-14 does. So carbon-14 changes into nitrogen-14, converting one of its neutrons into a proton and emitting an electron. That's beta decay. You could also have the opposite. You could have a proton turn into a neutron and emit a positron. And then you have gamma decay, where, for example, energized lead-204-82 decays to ground state lead-204-82 and it releases a gamma ray. So if you look at this, in all of these, the sums of the mass numbers on one side equal the sum of the mass numbers on the other, and the sums of the atomic numbers will be equivalent on each side as well, as long as you make sure to note that an electron has an atomic number of -1. And if you have a positron, which is an anti-electron, it would have an atomic number of +1. So uranium-238 undergoes alpha decay. What this does is it'll be radium-238 spitting out a helium nucleus. And this gives you thorium-234 and a helium nucleus. So uranium-238 decays to thorium-234. So here are the 5 common forms of nuclear radiation. You can have an alpha particle, a beta particle, a gamma ray, a positron, or a neutron. And these are the charges and the mass numbers. And so you'll have this process of decay. So here, for example, is the process by which uranium-238 will decay to lead-206. So we'll undergo alpha decay to thorium, the beta decay to 2 beta decays back up to uranium-234, then alpha decay to thorium to radium, uranium, I think, then polonium, lead, business, polonium, lead, bismuth, polonium, and then finally down to lead-206. So this is sort of the process by which uranium-238 goes down to lead-206. Now, which nuclei are radioactive and which are stable? We find there's certain patterns. Most stable nuclides have an even number of both protons and neutrons, even nuclides. And most unstable nuclei have an odd number of both protons and neutrons, odd nuclides. So a nuclei would be radioactive if its atomic number is greater than 83. If the number of neutrons is less than the number of protons, with two exceptions, which are atomic hydrogen and helium-3. But otherwise, if the number of neutrons is less than the number of protons, or if it is an odd nucleotide, with a few exceptions. Again, all very small. Deuterium, hydrogen-2, lithium-6, beryllium-10, and nitrogen-14. So smaller nuclei tend to be more stable. Stable nuclei tend to have about at the smaller end, tend to have about the same number of protons and neutrons. And they start to get unstable when, and then as you get bigger, you need more neutrons to be stable. So here, that's a typo, because that's not helium-86. This is one with fewer neutrons than protons. This is an odd. Even has 160 stable nuclei. Even odd has 52. Odd even has 52. And odd only has 4. So the pairing effect is very strong in stabilizing nuclei. So this is all the isotopes. And this red band is the band of stability. This black line is 1-to-1 neutron to proton ratio. And everything outside, everything that isn't red, all the blue dots are non-radioisotopes. Now, you can have nuclei can be more stable or less stable. And the way we express that is with the half-life. The half-life is the time it takes for half the nuclei in a given sample to decay, because the process of decay is random. So after one half-life has expired, only half the original amount of radionuclide remains undecayed. After 2 half-lives, a quarter remains. After 3, it's an eighth, and so on. So any radionuclide will decay with an exponential decay like so, where every half-life, the total number of the parent nuclei cuts by a factor of 2. So to find the number of half-lives, you can find the fraction of the mass. So what fraction of the mass of a 40 milligram sample of iodine 131, which has an half-life of 8 days, will remain in 24 days. So the first step is to figure out the number of half-lives that have passed in 24 days. 24 days divided by 8 days per half-life is 3 half-lives. We start with the given amount, 40 milligrams, and have it 3 times. So 40 divided by 8 is 5 milligrams. So after 24 days, there'll be 5 milligrams of iodine 131. Here's another example. Strontium-90 has a half-life of 29 years. So what fraction of strontium-90 produced in 1963 will remain in 2021? Well, 29 years. The time is 58 years, which is 2 half-lives. So we start with the given amount. 2 half-lives means we divide by 2 twice. So we start with our normal starting amount and divide by 4. So 1/4 of the original strontium-90 remains. And so how long would a sample of carbon-14 take to decay to 1/4 of its original activity? And the half-life of carbon-14 is 5,730 years.
So if it's going to cut to a fourth, that means it would take 2 half-lives. 2 half-lives, that's 5,730 years per half-life, is 11,460 years. And this rate of decay is something we can actually use to date things. So we can determine the half-life of a particular isotope by monitoring the activity of a known amount of that substance in the laboratory, and look at the rate of emission of the decay particles. And when the initial activity rate is fallen to a half, we've reached 1 half-life. This can be measured in a number of ways. It's usually measured with something like a Geiger counter. For things with a very long half-life, this has to be measured where you're not looking for a reduction by 1/2, but a reduction by a known amount. You can calculate how long it would take to get down to 1/2. So this is a Geiger counter. This is a device. The traditional Geiger counter has a container of argon gas. So when incoming radiation enters, it ionizes an argon ion that gives a small pulse of current, which is counted and amplified into a click. There are other ways you can do this detecting. I think these days they use scintillator material, which are solids that release light usually, or small amounts of current when they're hit by these particles. But it's the same general idea. And because of their constant decay rates, we can use radioisotopes as nuclear clocks. You can determine the age of objects that contain radioisotopes because you can know they had a certain amount when they started, and then know what they have now and figure out how much they decay. So a common one used for organic materials is, you may have heard of carbon dating. Carbon dating uses carbon-14, because it turns out anytime something is alive, in general, it exchanges carbon with its environment. You're doing that right now by breathing. And as you exchange carbon with your environment, you get new carbon in and old carbon out. It turns out that carbon-14 is continuously replenished by cosmic rays and the solar wind and stuff hitting the upper atmosphere. So if you're constantly exchanging with the environment, your carbon-14 level remains constant until you die. When you die, you stop exchanging carbon with the environment. So your carbon-14 will start to decay. And so all living matter contains about the same amount of level of carbon-14, or an activity level of about 16 counts per minute per gram of total carbon. In actuality, it's more complicated than that, because it turns out that level may have varied over time, the history of the Earth, and some living things get older carbon than others. Because it turns out, like fish or things that live underwater, it takes a little longer for them to interact with the atmosphere, stuff like that. But, in practice, it's more complicated than that, but that's the general idea. And then once something dies, it ceases to take in carbon-14, and so the carbon-14 within it will start to undergo radioactive decay. And therefore, the longer an organism has been dead, the lower the radioactivity of each gram of carbon, because carbon-12 and carbon-13 are stable, they're not radioactive in its remains. So by measuring how much carbon-14 is in a sample of something compared to carbon-12, you can figure out how long it's been around. And amusingly, this also applies to certain laws in the US. It is illegal for alcohol sold in the US to not be radioactive. That is because it is required that all alcohol sold in the US be made from plants and not oil. Oil has been underground so long, all the carbon-14 is decayed. So it's not radioactive. So your alcohol has to be made from plants, living things, which were exchanging carbon with the environment, and so will be radioactive. So there is actually a regulation, and you can get in trouble if the booze you produce isn't radioactive. It's one of the more amusing things out there. But yes, cosmic rays from outer space and the sun and stuff form neutrons. They react with nitrogen-14 atoms to make carbon-14. The carbon-14 reacts with oxygen to form carbon dioxide. Plants acquire the carbon dioxide during photosynthesis. That the plants are then eaten by living things. And when the organism dies, no more carbon-14 is acquired. And the carbon-14 decays radioactively with a half-life of 5,730 years. Now, in practice, carbon dating gets a little more complicated because it turns out certain diets lead to like older carbon entering your body. So if you eat a lot of fish, the carbon in your body is going to, you'll have a little bit less carbon-14 because fish get the carbon a little slower. But that's the general idea. So after about 10 half-lives, very little carbon-14 remains, and it's barely measurable. And the limit of radiocarbon dating depends on the ability to measure very low activity in old samples. So our current limit for carbon dating is somewhere in the 4,000 to 5,000 years. Now, I think we've gotten a bit better than that since this slide was right. But that's sort of the 40,000 to 50,000 years is about the limit. So if you find an old scroll in a cave that has a carbon-14 activity of about 4 counts per minute per gram of total carbon, you get 4 counts per minute, that's a quarter of the normal rate. So that's 2 half-lives. Carbon-14 has a half-life of 5,730 years. So the scroll would come out to 11,460 years. This scroll would be between 11,000 and 12,000 years old. This example is not accurate because that's crazy old for a scroll. Writing isn't that old. But yeah. So we know radioactive nuclei can spontaneously change into the nuclei of other elements. This is a process called transmutation. And scientists wondered if we could do the opposite. So we know that basically elements can decay down into smaller elements, but could we add stuff to elements to make things go up? And the answer to this is yes. And this process is called a nuclear reaction. So it is possible to do the classic, the rumored, alchemical process of changing lead into gold. I don't think it actually has ever been technically done with lead. It was done with bismuth, which is next to lead on the periodic table. And the cost required is ridiculous. Like trillions of dollars per gram or something. But it has been done. So in 1919, Ernst Rutherford produced the first nuclear reaction by bombarding nitrogen with alpha particles. The result was an artificial transmutation of a nitrogen isotope into an oxygen isotope. You got helium plus nitrogen gave you oxygen 17 plus a proton. This is actually a reaction that happened. I think this is actually a reaction that can happen in stars. Again, mass number is conserved and atomic number is conserved. So the 18 is the total mass number on each side, and 9 is the total atomic number on each side. And the general form of a nuclear reaction is some particle bombards A, and you get B plus some emitting particle B. And again, these are the common particles involved. People use, in addition to the particles here, you get protons, deuterons, hydrogen 1,1, and oh, these are in the wrong place. This is a proton, this is a deuteron, this is a triton. They put their symbols in the wrong place when I describe this. I'll have to fix that slide in the future. So here, for example, if you bombard lithium-7 with a proton, It will emit a neutron. So the mass number on the right must also be 8, and the sum of the atomic numbers on the left is 4. So the atomic numbers on the right must also equal 4. And so you will get beryllium-7 coming out. That's the equation. Here, if you bombard aluminum with deuterium, you'll get an alpha particle out and magnesium-25. And Rutherford's discovery of the transmutation of nitrogen-14 into oxygen-17 was actually an accident. But the implications of the discovery were important, were enormous. One element can be changed into a completely different element. And the dream of the alchemists has come true. It's now possible to actually make gold from other more common elements. And this was actually done. They bombarded yeah, I think it was beryllium. No, it was bismuth. They bombarded bismuth in a particle accelerator to make gold from it. This process is millions of dollars. It's actually like, I don't remember the cost worked out. It's a ridiculous number. They made a tiny, tiny amount, a handful of atoms. And the cost was not cheap, because they had to use a particle accelerator. So well over $1 million an ounce. It's more like $1 billion an ounce. I don't remember the actual numbers. So neutrons produced in nuclear reactions can be used to induce other nuclear reactions. So it's possible to have a chain reaction, where one reaction sets off another one, and so on. And since neutrons don't have an electrical charge, they're particularly good at penetrating the nucleus and causing a reaction, because nothing pushes them away. So without electrical charge, they're not influenced by positive and negative atomic charges, so they're not driven away from the nucleus. So elements past uranium with an atomic number greater than 92. This is not technically correct. You can get a small amount. It was thought for a long time that all of these elements were synthetic. And they sort of are. But there actually there's a tiny amount of plutonium created naturally in uranium deposits by nuclear reactions. But yeah, generally we get plutonium, and anything past 92 is generally created by bombarding elements with a lighter nucleus with alpha particles and neutrons, or sometimes even heavier. For example, you can bombard uranium-238 with a neutron and get neptunium-239 and an electron. So part of the issue is that most of these things that are heavier than 93 are also they don't last that long. So if they were around, they would have decayed. So they have to, but apparently there's a tiny amount of like plutonium and neptunium in uranium deposits being created by reactions like this. Or you can have, say, iron and bismuth, and you slam them together, you can get, I don't even know the name of this off the top of my head. 109, element 109, and 266 on a neutron. So here's sort of the process we got all of our elements. Hydrogen, helium, and hydrogen and helium, most of the hydrogen and helium in the universe was formed during the Big Bang, along with a tiny amount of lithium. Interestingly enough, all the helium, none of the helium that is on Earth that we use came from the Big Bang. All the helium on Earth that we use came from the radioactive decay of other elements. Because it's an alpha particle. It's also why it's rare and expensive. Basically, Earth's gravity isn't strong enough to hold on to helium. So any helium in the atmosphere we use. However, most of the hydrogen that makes you up came from the Big Bang. A tiny amount of lithium was formed in the Big Bang. Most lithium was formed by other processes involving supernovas. Stuff from beryllium up to iron was likely made in the cores of stars by fusion. I think beryllium's kind of skipped, actually. Beryllium and boron are a little harder to make. And then atoms heavier than iron are thought to be formed during supernova explosions of stars, when there was an abundance of neutrons and where there's abundance of neutrons and medium-sized atoms. There's all that energy that can cause things to get bigger. You get energy out with fusion up to iron. Past iron, you don't. So those don't happen on their own. You need to have energy from somewhere else. Now, radionuclides are incredibly useful. We use them all the time. We use them in medicine, chemistry, biology, geology, agriculture, industry. So one example of medicinal use is a radioactive isotope of iodine, iodine-123. We use it for diagnostics of the thyroid, diagnostic measurement of the thyroid gland. So a number of radioactive elements are used for diagnostics because, you eat them, they travel through your body and emit radiation, and you can detect that radiation and use that for imaging of systems that use that element. Unless you these things, you wouldn't be able to otherwise. You can also use it for emitting radiation to kill things you want to kill, stuff like that. And for another thing, americium, why am I saying americium, named after America. I'm just miserable at pronouncing this name. Americum 241, which is it's an artificially created uranium nucleotide, but you probably have some in your home because it is used in lots of smoke detectors. So the smoke detectors work. There's a small amount of americium 241, which is emitting radiation. And if smoke comes in, that radiation gets blocked, and that sets the smoke detector off. Though not all smoke detectors use that, but it's very common. So basically, it's a weak radioactive source. It ionizes the air, sets up a small current. And if smoke particles enter, the current is reduced, and that sets off an alarm. Because the smoke basically gets in the way. And then in chemistry and biology, it's really useful to use radioactive nuclei as tracers, because you can detect them. So radioactive tracers like carbon-14 and tritium, hydrogen-3, are used to tag an atom within a molecule. This way, the reaction pathways of drugs and hormones can be determined. You can see where the actual atoms are moving around. And in geology, we use the predictable decay rate of radioactive elements in rocks and minerals to allow age determination. In industry, tracer radionuclides help manufacturers test durability. And then in some things, we use radioactive decay to excite phosphors to make things glow. Though not so much anymore, because we used to use stuff that was very toxic in its own way. So they used to use radium for this, which was a bad idea. They used to put it in paint. It wasn't like the things weren't so bad to have. The radium is pretty radioactive. The problem was they didn't have good safety treatments. And so the people who were painting these things with this radioactive paint weren't told anything about the dangers and were doing things like licking their paintbrushes. And so the radium was entering their bodies, replacing phosphorus, I think, in their jaws, or replacing things. It caused horrible, debilitating problems. But another thing that was used is they used tritium, hydrogen-3, in gun sights to have glowing dots for guns. And then there's nuclear fission and fusion. Nuclear fission, so we talked about, like, we can make atoms get bigger by adding something to them. We can make atoms get smaller by having them squirt out a small amount. Nuclear fission is when an atom splits in half. And this usually also involves the emission of neutrons and conversion of some of the mass into energy. So the classic nuclear fission is uranium-236 fissions into two smaller nuclei, emits several neutrons, and releases energy. Uranium-236 is formed when uranium-235 gets hit by a neutron. So what we use to cause this is uranium-235. So you get 4 additional units of mass needed on the right, 4 neutrons are released. This is 4 neutrons. And here's uranium-236, putting the strontium in 2 neutrons, and that's a xenon-54. And the products of fission are always radioactive. Some of the products have half-lives of thousands of years, and this can lead to the problem of disposing of nuclear waste. But honestly, the main problem with disposing of nuclear waste is that people are way more afraid of nuclear material and nuclear waste than they need to be. But relatively large amounts of energy are produced and neutrons are released when you have nuclear fission. And one of the things is that you can have a chain reaction. One initial reaction triggers a growing number of subsequent reactions. In the case of uranium-236, each fission emits 2 neutrons. And each of these neutrons can hit another uranium-235, leading to the fission of a 235 nuclei and the release of energy in 4 neutrons. And this causes an expansion of the chain. And this will happen spontaneously if you have enough uranium-235. So you have uranium-235, it's hit by a neutron. It forms an unstable uranium-236 with splits into strontium and xenon, which makes 2 neutrons, which can then hit more uranium-235s and so on. And we can control this process to generate electricity. So if all the emitted neutrons hit another uranium-235 nucleus, this results in an increasing number of emitted neutrons, fission reactions, and energy release. And this is an expanding chain reaction. And if you set your thing up so that this happens, that all your neutrons are going to hit other uranium-235s, you can get a situation where you can get a steady state, a self-sustaining chain reaction, where you achieve a steady release of energy when each fission event causes, on average, only 1 more fission event. That's self-sustaining. For a self-sustaining chain reaction, you need the correct amount and concentration of fissionable material. Uranium-235 needs to be present. If there's too much present, you get an expanding chain reaction. If there's too little present, the chain reaction will come to a stop. And it turns out, to make that happen, what you can do is you can sort of adjust the speed of the neutrons so they're more likely to run into another 235. And that's what they do in nuclear power plants. And so there's some minimum amount of fissionable material necessary to sustain a chain reaction. This is called the critical mass. About 4 kilograms for pure uranium-235. If you have less than that, you're not going to get a chain reaction. If you have more than that, you get an expanding chain reaction. So natural uranium is about 99.3% uranium-238 and about 0.07% 235. So in order to make a sustained nuclear reaction, you need to enrich the uranium. You need to increase the amount of uranium-235. In US nuclear reactors, uranium-235 has been enriched to about 3%. That's enough for a self-sustaining chain reaction. In contrast, if you want a out of control chain reaction that is quite violent, known as a nuclear bomb, you enrich it to something like 90% or more for a sudden release of energy. That's how you make a nuke. So in order to create a fission bomb, an atomic bomb, you use a supercritical mass of fissionable material that needs to be formed and held together. So basically what you have is you have two lumps of fissionable material that are subcritical, held apart until you want them to go off, and then you slam them together. And then that's a conventional explosion brings the subcritical segments together to create a supercritical mass capable of an explosive release of energy. This is one of the ways you can make a nuclear bomb. The other way, this sudden energy release is due to an expanded chain reaction of fissionable material. The other way, you can take a just short of subcritical mass, and then you can implode it. And as it gets denser, it ends up being supercritical. So that's the other way you can make a nuclear bomb. Turns out the very first nuclear explosion was that kind. Mainly because it was the harder one. So they wanted to make sure it would work. And then I believe the first one dropped on people was the gun type, where the two subcritical halves slammed together. But the Trinity explosion, the world's first nuclear explosion, was an implosion. So nuclear reactors, on the other hand, need to have a controlled and continual release of fission energy. You don't even want things to go out of control. So within a reactor, so the stuff in a nuclear reactor cannot cause a nuclear explosion. So you have long fuel rods and control rods. So the fuel rods contain a fissionable material, and the control rods contain a neutron-absorbing material, such as boron or cadmium. And these control the rate of nuclear fission by basically absorbing all the neutrons and preventing them from causing more fission. You can also add materials that are called moderators that they slow the neutrons down but don't absorb them, and then make them more likely to interact with the uranium. And so this is sort of a conventional nuclear reactor. You have control rods and fuel rods in a big tank of water. And the basic idea, like almost all conventional power plants, they boil water. The vast majority of our power generation works by boiling water. The nuclear reactors boil water. These fuel pellets of uranium oxide get very, very hot. They heat up the water. The water is boiled and generates steam. So you have pressurized water that goes out to the steam generator and pressurized water that comes in from the steam generator. So the fission rate in the fuel rods cannot be directly controlled. The control rods are inserted or withdrawn to control the number of neutrons being absorbed. And the reactor core is basically just a bunch of hot rods, spicy rocks. The heat is continually removed by the coolant flowing through the core, and this is used to generate steam in a steam generator, like a coal power plant or a gas power plant or many other power plants. Usually there's actually two circuits. You have hot water running through the reactor, which heats other water, which turns to steam and flows through the steam turbine. That isolates the water that's exposed directly to radiation, radioactive material. And that's completely changed, so there's no radioactive contamination. The water performs two critical functions. It transfers heat from the reactor core to the steam generator, and it serves as a moderator. What moderators do is they slow down neutrons to make them more efficiently cause uranium-235 fusion. So after colliding with several oxygen molecules, the neutrons have slowed enough to induce uranium-235 fission more efficiently. basically. And there's some dangers with continuous fission chain reactions, but they are in fact the safest form of power generation out there. You know, the number of people who've been killed by nuclear power plants, is, maybe a couple dozen in the entire history of, compared to things like coal. Coal power plants emit more radioactive material than nuclear power plants. So the amount of heat that's generated needs to be controlled. The fission rate is controlled through the insertion or withdrawal of the control rods. And the heat generated needs to be continually removed by the circulation of the coolant. So that's sort of the engineering problem. And improper control or removal of core generated heat can lead to the fusing or meltdown of fuel rods. This is bad. And the uncontrolled fissioning mass will become extremely hot and literally melt through the floor of the containment structure. This has happened once. Well, actually, it's happened a few, but once on a large scale, which was Chernobyl. Chernobyl was a full meltdown. So at this point, the extremely hot and uncontrollable radioactive material enters the outside environment, and that's bad. So 3 large-scale nuclear accidents have occurred. There's been a few small ones with like test reactors and stuff, mostly like back in the 50s and 60s. 3 Mile Island in Pennsylvania in 1979. An accidental shutdown of coolant led to a partial meltdown, and it was basically entirely contained. Nothing dangerous. It was a big scare, but nothing dangerous was actually released. Chernobyl was a long, extended series of F-ups. But a complete meltdown occurred due to poor human judgment and design problems. 3 Mile Island was a whole bunch of design issues. Like they weren't consistent on what color meant warning. They had too many warnings, and it wasn't consistent. Well, like if a light was on, was it a good thing or a bad thing and stuff. Like their interface was really poorly designed. Chernobyl, they had turned off important safety systems. Like just whole mess. And then everybody panicked and basically ran away. So there was an explosion and a fire in the reactor core and significant regional contamination. It was bad. And then there was Fukushima in 2011, where a severe earthquake caused power loss. Basically, the backup generators to circulate coolant lost power. And tsunami waves disabled, because the tsunami waves disabled the backup generators. And this resulted in a partial exposure of 3 reactor cores. Hydrogen gas was generated and exploded, and that led to the release of radioactive material. But again, like the number of people who died in these accidents, very little health damage in total. Like there were a few people, definitely some people at the cleanup of Chernobyl were dangerously exposed. Chernobyl was bad. But no one died at Fukushima from Fukushima. Now, another thing we can use, so behind uranium-235, another fissionable nucleotide is plutonium-239. Plutonium-239 is produced by the bombardment of uranium-238 with fast neutrons during the normal operation of a nuclear reactor. And a breeder reactor is a reactor designed to produce plutonium-239, where you get, it's not designed to produce a lot of power, it's designed to produce a lot of plutonium. And then the plutonium-239 is later separated and then can be used in an ordinary nuclear reactor, or more commonly in nuclear weapons. But there's also a number of things that are produced in breeder reactors that are useful outputs of them that we use in medicine and other things. But plutonium-239 is a natural byproduct of a nuclear reactor. And 20 breeder reactors running for a full year produce enough plutonium-239 to run another reactor for a full year. So breeder reactors run at a higher temperature than conventional reactors, and they use liquid sodium as a coolant. There's various new designs for reactors that use liquid sodium or liquid salts for coolants as well. Pebble bed gas reactors are a possible next generation for nuclear reactors. They use graphite uranium pebbles instead of fuel rods. And the reactor is cooled by non-explosive helium gas instead of water. Helium is inert, it doesn't become radioactive, and graphite is a good moderator for slowing down the fission neutrons. And they're designed to dissipate heat on their own and can be shut down by removing the pellets. Basically, pebble bed gas reactors are designed such that they can't melt down. And I think China has developed, it just about started having one or has a test reactor for a pebble bed reactor running now. Like just recently that happened. Now, what would be better is if we could do fusion. This is the process by which smaller nuclei combine to generate larger nuclei, along with the release of energy. This doesn't require a critical mass, but it does require a bunch of starting energy to make it happen. The fusion is the source of energy of the sun and other stars. And in the sun, the fusion process that produces a helium nucleus from 4 hydrogen nuclei. You get 4 hydrogen nuclei in a multi-step process combined to generate a helium nucleus, 2 electrons, 2 neutrinos, some gamma ray, a couple of gamma rays, and some energy. And this is actually like a multi-step process. You first get hydrogen fusing into deuterium, then deuterium turning into helium-3, and then helium-3 fusing into the hydrogen. It's like a 3-step process. So you get for this process, the first step is 2 helium nuclei formed to form deuterions. The deuterions, 2 deuterions form to form a tritium and a proton. That's a deuterium. So some examples of fusion reactions. These are the ones that are considered for actual process of things like deuterium-deuterium fusion, where 2 deuteriums fuse to form tritium and a proton, or deuterium-tritium fuse to form an alpha particle and a neutron. And that's not the process that happens in the sun, but these are the ones that we're planning to use on Earth, because they're much easier to actually do. So this is the deuterium-tritium fusion reaction. Deuterium, tritium combined, you get hydrogen and a neutron. Oh, this is out of power. Okay. Now, nuclear fusion is hard because you're slamming 2 positively charged nuclei together. They don't want to be together. So the repulsive force between positively charged nuclei is very great. To overcome that repulsive force and initiate fusion, you have to heat them to incredibly high temperatures, like 100 million Kelvin. And at these temperatures, the hydrogen atoms exist as a plasma, gas of electrons and neutrons. So it's not that hard to cause fusion on Earth, but to get more energy out than you put in is hard. So the plasma has to be confined at a high enough density for protons to frequently collide. And even with today's technology, it is a significant challenge to reach the necessary temperature and confinement requirements to actually get more power. No one has successfully gotten out more power than they put in a controlled manner. We have gotten out more power than we put in, but we do that in an uncontrolled manner. It's called an H-bomb. So what you can do is you can use an atomic bomb to set off this process with deuterium and tritium and make a real big boom. So inertial confinement is where simultaneous high energy laser pulses from all sides cause a pellet of deuterium and tritium to explode, resulting in compression and high temperatures. If a pellet can be made to stay intact for a sufficient time, fusion is initiated. And this is research into this is being conducted at Los Alamos and Lawrence Livermore labs. This is mostly happening because it's very helpful for designing nuclear weapons. It's not really viable as a power source because it's hard to get the energy out. The serious power generation people are doing magnetic confinement, where because this stuff is so hot, it's a plasma, so everything involved is charged. So you can make a donut-shaped magnetic field that holds the plasma and keeps it from touching anything, and allows you to get it incredibly hot. So you use magnetic and electric fields because plasma gas is a gas of charged particles. And the leading research for fusion research using magnetic confinement in the US are done at MIT and Princeton. But the big research on it is being mostly done in Europe. Like ITER is the big, developing a tokamak reactor. So fusion has a bunch of advantages over fission. Deuterium is readily available and cheap. You can get it cheaply from water. You can literally get it out of water. The waste produced by fusion is much less and much easier to deal with. Relatively few radioactive byproducts are involved. They all have relatively short half-lives. So if you just keep them in one place, isolated for a little while, they'll stop being a problem. And fusion reactors can't get out of control. In the event of a system failure, they lose containment and all the fusion stops. And everything quickly cools down. It's not dependent on critical mass. So fusion reactors don't go boom. And it turns out nuclear reactions are interestingly tied to some of the ideas from Einstein's special theory of relativity. It deals with things moving very, very fast. The changes that occur in mass, length, and time as an object approaches the speed of light. And it predicts that mass and energy aren't separate entities, but are related to each other by the famous equation E equals mc squared. And it turns out nuclear reactions are one of the ways you can see this. Einstein's predictions are proved today correct. We're able to change mass into energy and on a very small scale, energy into mass. So the equivalent energy of 1 gram of mass is about 90 trillion joules. That's the same amount of energy released by 20,000 tons of TNT. And one of the interesting things that happens in a nuclear reaction that generates energy, the mass of the starting material is slightly higher than the mass of the ending material. So calculations with Einstein's formula, E equals mc squared, have shown that small amounts of mass that are lost in nuclear reactions would be a tremendous source of energy. And to determine the change of mass in a nuclear reaction, we simply add up the masses of the reactants and subtract the masses of all the products. And generally during a nuclear reaction, mass is either gained or lost. So for example, in that fusion process, where you start with 4 hydrogen nuclei and end with helium nucleus, 2 electrons, and 2 neutrinos, mass is lost. The end products have less mass than the starting products, and that comes out as energy. And the mass defect is usually measured in mega electron volts. And if you have an increase of mass during the process, that is an endogaric reaction. It absorbs energy. It absorbs energy by the number of atomic mass units times 193, 931 mega electron volts per atomic mass unit. And exogeneric, if you have a decrease in mass, it releases energy at the rate of 931 mega electron volts per atomic mass unit. So for example, here, uranium-236 to the krypton-88 and beryllium-144 releases, and 4 neutrons. The total mass on the left side is 236.00556 mass units. On the right side is 235.87197 mass units. So the difference is 0.17359 mass units, and you get 162 mega electron volts of energy released. And here we have deuterium-tritium fusion goes from 5.031 mass units to 5.0113 mass units. So the mass defect is 0.188 units, so 17.5 mega electron volts of energy are released. But the starting material is much lighter than the previous thing. So this is actually a much more efficient reaction. So on a kilogram for kilogram comparison, you get more energy from fusion than from fission. The fission of 1 kilogram of uranium-235 produces energy equal to the burning of 2 million kilograms of coal. Hence why nuclear power plants are a great way to help save our environment. And the fusion of 1 kilogram of deuterium releases energy equal to the burning of 40 million kilograms of coal. Why fusion would be a much better source. But fusion's just technically much harder. So it's not happening right away. So we should make more fission power plants because we can make them better safe. So these are the energy release per atomic mass unit of these things. So any reaction that ends up upward on the curve releases energy because the reaction is calculated by mass defect. This is the relative stability of the unit. This is the mass number of the nucleus. This is the mass per mass number kind of thing. And you can see here, iron is the most stable nucleus. So the general tendency is for stuff to go to iron 56. So when a star doing fusion in its core, when a really big star doing fusion in its core ends up with a core of iron, it stops being able to do fusion, that core collapses, and the star explodes in a supernova. So fission proceeds from right to left, fusion proceeds from left to right. And at the top of the curve is iron 56. You get no energy released by either splitting iron 56 or fusing several iron 56. Now, radiation has effects on biological stuff. Ionizing radiation is radiation that's strong enough to knock electrons off of atoms and form ions. And this can be bad because it can break molecules or cause reactions you don't want to have happen. So ionizing radiation includes things like alpha particles, beta particles, gamma rays or gamma particles, neutrons, gamma rays. Gamma particles and gamma rays are the same thing, and X-rays. And these types of radiation can also harm or kill living cells, and they're especially harmful if they affect molecules involved in cell reproduction. And some ultraviolet light can also be ionizing, but not quite as much. And you have no method of detecting ionizing radiation. It can't be seen, smelled, felt, or tasted. The common way we detect it is with film badges worn by workers. They're commonly used to measure radiation exposure. And the effects of radiation on living organisms can be classified into 2 categories. Somatic effects, which are short and long-term effects of the recipient of the radiation. The damage caused to you by the radiation, and genetic effects. They're defects in the recipient's subsequent offspring. The radiation can damage the cells that you use to pass on your genetic material, and that can screw up your offspring. There's like 3 million different units for measuring radiation exposure. It's really kind of unfortunate. But the REM, the Röntgen equivalent for man, is the unit used to discuss biological effects of radiation. This unit takes into consideration the relatively ionizing power of each type of radiation and its effects on humans. And the average US citizen receives around 0.2 REM per year from a number of different sources, both natural and man-made. Like, no matter what, you're going to be exposed to radiation. There's radiation coming from space. There's radiation coming from various just naturally occurring radioactive elements, like bananas have radioactive potassium in them, things like that. Not a huge deal. But for example, if you go on an airplane flight, you're going to get more radiation than you would if you didn't. Because you're higher up, the atmosphere is blocking less of the radiation from space. So these are the average annual radiation exposure for a person in the US. The most common source is radon coming out of the ground. Then we have other radiation from soil and rocks, internal radiation within your body, cosmic rays, and then these are human-made. Things like medical x-rays, nuclear medicine, various consumer products, and then another 1% or so. Oh, it's 3:15. Let me finish this off quickly. So natural sources of radiation, things like cosmic rays, the bedrock, radionuclides that are ingested, radon gas from bedrock, which varies greatly from location. That's the most common source of radiation in the US. And then there's anthropogenic sources like medical x-rays and treatment, TVs, tobacco smoke, nuclear waste, burning coal, things like that. And the long-term cumulative effects of radiation exposure aren't fully understood. And the most common long-term somatic effect is an increased likelihood of getting cancer. And many early workers of nucleotides died of cancer. And these scientists were generally exposed to small doses for many years. So Madame Curie got cancer. Her husband, whom she also worked with, did not die of cancer, but that was because he got hit by a streetcar. They were, did some of the very early radioactive work. They were exposed to lots of this. And the penetration of radiation, we don't really understand radiation stuff, but it appears there's not a lower limit on which the effects are negligible. But so any exposure to radiation should be generally taken seriously, but you shouldn't panic. But things like alpha and beta rating particles, they get stopped easily because they're electrically charged. Like your clothes will stop alpha and beta particles, and a reasonable amount of air will do it. But things like gamma rays, neutrons, and X-rays are much more difficult to stop because they're not charged particles. And then there's some debate whether small amounts of radiation exposure is bad or not. There's a lot of debate about that. But we've also found other elementary particles than the 4 subatomic particles we imagine, the electron, proton, neutron, and photon. There are more than 200 elementary particles. So there's the exchange particles responsible for the 4 fundamental forces. There's the things that things like neutrons and protons are made of, quarks. There's a bunch of other things like neutrinos and things like that. And particle accelerators are used to study elementary particles. So the Large Hadron Collider is the big one in Europe. It's near Geneva. The biggest one in the US is at Fermilab. It's near us. It's out in the western suburbs. This is the Large Hadron Collider is the largest particle accelerator built so far. And we found the Higgs boson. Every particle has an antiparticle. The wider particle of electron is the positron, for example. And when particles and antiparticles mix, they annihilate each other and release energy. And that's the end of the chapter. It's free to go. And remember, you have the chapter 7 quiz today in SI. Sorry that ran kind of long.